Okay, thank you for the introduction, and thanks for the organizers for giving me the opportunity to present our results here. So I'm from the group of Monica Schleyer-Smith, and I'm a postdoc there. And so what I'm going to show you today is how we use basically this optical cavity to generate interactions that are programmable between atomic ensembles, so between neutral atoms. And so afterwards, I will also show you how we can use these interactions to engineer some interesting entangled states inside the system. So let me first start by introducing a bit neutral atoms. So they are a very nice system, and they have found a lot of applications, like for example, in quantum simulation, which this is just a short small subset. So you can use it, for example, in optical lattices to simulate condensed matter systems. And to get to superconductivity, or you can study out of equilibrium dynamics. Then on the other application, they are used in metrology as very good sensors for magnetic fields or inertial sensors. And the nice thing is that you can also entangle them, and then they become even better sensors. And one that gets the most attention recently is that you can also use them for quantum computation. In a way that we also heard yesterday in Loic's talk, is basically that you use them in these tweezer arrays, and you can shuffle them around and use entangling gates between them. And with that, you can do kind of quantum computation with it. And the reason why neutral atoms are so successful and interesting in these areas is, so one reason we already heard yesterday is that they're very scalable. So you can prepare single atoms, you can prepare 1 million atoms, and you can trap them in these optical dipole traps, which gives you a lot of control over the potential you have. So you can use all the tricks you have from optics to make these fancy potentials. And then after you do your experiments, of course, you always want to get information out of the system. And for that, you also have a variety of readout systems. Here's an example of a quantum gas microscope where you can really image individual atoms, and you can also do it in a state selective way. And also you can do single particle control on them. So you have a wide variety of readout methods and controllability over your system. But now there comes always the downside of neutral atoms. And this is that if you want to simulate something interesting, you want some interactions that are interesting. And typically, neutral atoms are very weakly interacting, though most of them just interact via short-range collisional interactions. And you have to do some fancy tricks to get them more interacting. For example, you can excite them to a high electronic state where they become effectively bigger, and you get some longer range interactions, or you can use some dipolar interactions. But these interactions are still kind of short range in the sense that, for example, if you look here and you want to somehow use a higher dimensional, you want to make a higher dimensional connectivity graph, for example, where you connect the tip of this cone to the base of this cone, then what you need to do is basically you would need to shuffle the atoms to the bottom and then let them interact, shuffle them back, which you can do, but it's experimentally not easy. So the goal of our experiment is to introduce interactions that are really programmable and where you can get to very high dimensional connectivity graphs between the atoms. And like I mentioned in the beginning, what we use for that is an atom cavity system. So I will first give a short introduction about a cavity QED, then how we use these interactions to get to a programmable system, and then in the end, how we use these programmable interactions to actually get to quantum correlation and entanglement. Okay, so the basic idea of cavity QED is, suppose you have two atoms, and as we heard, they are not very interacting. So suppose they are both two-level atoms, and one of them is in the excited state, then a nice way to make them interact is if one of them decays and emits a photon, if the other one would just pick up this photon. And of course, you all know this is very rare to happen. So the basic idea is just put two mirrors around that and let it try again and again. So just let the photon bounce around 10,000 times, and then the likelihood that the other atom will absorb it is increased. So basically one atom emits the photon now into the cavity mode. And the important parameters for this system is the coupling between the atom and the cavity, which is G. Then there are also some decay process. For example, you can lose the photon, which is given by the cavity line with kappa. And there is some scattering rate gamma, which basically tells you how likely it or what the rate is that the photon will be emitted outside of the cavity. And then the figure of merit in all of these cavity QED systems that you want to optimize is this cooperativity eta, which is just the ratio of your coherent coupling G squared divided by your loss process, which is gamma and kappa. And to go to a really quantum regime, you want this number to be much larger than 1. And just for a little bit experimentally, basically you can rewrite this, and if you want to plan a cavity, then what you want to do is you want to have a very small waist at the position of your atom, basically to increase the overlap between the waist and your cross-section of the atoms. Okay, and so let me now introduce our system. So we have a cavity that's about 5 centimeters long, which is pretty macroscopic, and it supports 2 wavelengths. And one wavelength it supports is this 1560 nanometer wavelength, which we use to make a lattice of 1560 in there. And then the atomic species we use is the simplest you can find as an experimentalist is rubidium-87. And so on the right side, there's everything you need to know about rubidium-87 for this talk. Is basically it has 2 electronic states, which are separated by about 780 nanometer. So 1560 is far ready-tuned from that. So the atoms will collect at the antinodes of this lattice inside the cavity. And then to make it interact, in the ground state, rubidium also has 2 hyperfine manifolds, and we concentrate on the Fx equals 1 hyperfine manifold, which has 3 magnetic substates, +1, 0, and -1. And these magnetic substates are split by a magnetic field, which in our case gives an energy scale of 1.4 megahertz. And so for the interaction, the cavity supports a second wavelength, 780 nanometer, which is very close to the transition frequency of this atom of rubidium-87, but it's detuned by 11 gigahertz. And I will explain in a minute why and how this induces interaction. And so just here are some cavity parameters if you're interested. And the important figure is that we have a cooperativity about 4.5, which is not much bigger than 1, but it's good enough to see quantum effects. And then, so we need another thing to introduce interactions, which is basically we have to drive the cavity. And we drive it off resonantly in such a way that if you would add up a photon from the cavity and from this drive field, we are a little bit detuned from 2-photon resonance. So if you would tune this to 2-photon resonance, you would just flip atoms from 0 to -1, for example. But we are detuned, and I will explain in a minute how this introduces interaction. Let me just first show you how this looks like in the experiment. So this is our vacuum chamber. Here is one of the mirrors of the cavity. Here's the other one, which has a little bit fancier holder. And the rest are reflections. And here there are windows, basically, to just get optical control to put atoms in the middle of the cavity. Okay, and so for the interactions, let's say I have here my ensemble of atoms, and now we just focus on any 2 of these atoms. And we prepare them in the MF equals 0, so in the ground in MF equals 0 magnetic substate. Now, as I said, we drive the cavity, and now the process where an atom absorbs a photon from the drive field and emits one into the cavity field, this is off resonant. So you can't do just a single atom spin flip. But what we can do, because the cavity enhances these atom-light interactions, you can do a 4-photon process, which is basically one atom absorbs a photon from the drive field, emits a photon into the cavity. This photon bounces around inside the cavity, can be absorbed by another atom, and this atom then emits a photon into the drive field again. And so by that, energy is conserved on the photonic side because you have not changed the number of photons in your drive field and in the cavity. And also on the atomic side, it's conserved because the Zeeman shift is basically symmetric. So you can do this 4-photon process, and by that mediate kind of this pair creation process where 2 atoms in 0 change to an atom in +1 and an atom in -1. And you can write down the Hamiltonian for this, which is this flip-flop Hamiltonian. And if you want, you can also rewrite this in another way. If you're more familiar with XY Hamiltonian, then this flip-flop Hamiltonian is also an XY Hamiltonian in this spin space. So where you the spin in x direction interacts with other spin in x direction. And the nice thing about the cavity system is you can tune the sign of the interaction. So by changing this detuning here, you can change from anti-ferromagnetic interaction to ferromagnetic interaction. And we usually work in a regime where we are highly ferromagnetic interactions. So the main takeaway from this slide, if you don't like the 4-photon process, is you can get rid of it and just say, okay, we drive the cavity, and by that we induce this pair creation process among the atoms. And this is inherently long range because it's mediated by the cavity field. Okay, so now let's see how we use it to get to programmable interactions. So for that, we prepare now ensembles of atoms inside the cavity. And we prepare about 16 to 18 ensembles, and they are separated by about 60 microns. So the whole array we have is about 1 millimeter. And so each of the ensemble, we prepare the atom in the MF equals 0 state. And then, like I said before, we then drive it. And then this drive mediates this pair creation process where basically this pair creation can happen between any ensembles in this cavity. So it's an all-to-all interaction. And now we want to see how do you actually verify that it's an all-to-all interaction. And one thing you can do is you can look at correlations. And the nice thing about our cavity is that because it's so big, we have optical access to our atoms. So at the end of the experiment, we can take an image of our atoms and measure the population in the 0 and plus or minus 1 state, which is here a typical camera image. And here you see these 18 ensembles. And now we can look, how's the population of one ensemble in the +1, how is this correlated with the population of the -1 state in another ensemble? And for an all-to-all interaction, you would expect that they are highly correlated. And this is, in fact, what we see experimentally. So basically, if we do this measurement and take these correlations, we see just everything is correlated. Okay, so we have these all-to-all interactions. So they are nice, but we want to get something that's more programmable. And the first step for this is to trim down the all-to interaction to just a single side interaction. And the trick to do that is, if you now introduce a magnetic, so if you, instead of using a homogeneous magnetic field, you use a magnetic field gradient, then because this energy splitting here is magnetic field dependent, basically what it means is, if you go to a site that's different from your original site, this 4-photon process is off resonant. So this 4-photon process is then just resonant with atoms from the same ensemble. So you just get on-site interactions. And in fact, when we look again at the correlations, we see that it now reduced just to on-site interactions. And now the trick to introduce controllable interaction is basically to introduce a second light field, which just bridges this energy gap between like photons that are atoms that are like 3 sides apart, for example. And if we do this, we see in the correlation that these correlations pop up at one specific energy scale that we can put in experimentally. And so basically what we do experimentally, so the magnetic field gradient is typically 1.5 to 15 kilohertz per side. So we don't use an extra drive field, but what we do is we modulate the intensity of our drive field. And then in the frequency spectrum, you basically get these side modes, which we tune to bridge these specific energy gaps. And so if we tune the modulation frequency of our drive field, basically we can tune the range of our interaction from on-site interaction to distance 1 and all the way down along our atom chain. And to show how good we can control it, we can also zoom in on one of these ranges, and then we see that these are really discrete resonances. So we can really have interactions at distance 9, at distance 10, and they are very discrete. Okay. Now, this was just using continuous modulation of your tri-field. You can do more fancy things. So instead of having a continuous tri-field, one thing you can be more fancy is you can pulse it. And what this does is, if you pulse something in time space, you also, or if you have a Dirac comb in time space, you also get a Dirac comb in frequency space. So you basically just repeat this structure over and over again. And if you do it in such a way that this main peak here would correspond to an artificial site 0 that you put at the end of your chain. And basically, if you modulate it initially to have interactions at distance 3 and you pulse it, you also get interactions at distance 7. And you can also think about this in a different way. You get interactions at distance 3, and you got also interactions starting from the other side of the chain at -3. And so it's better not to think of this as an open chain, but basically as a system with periodic boundary conditions. And so this shows that just by changing the modulation of our tri-field, we can change the effective geometry of our system from a chain with open boundary condition to something with periodic. And if we tune again now the modulation frequency, we now find here this cross structure. And this is basically a signature that we now have a system with periodic boundary conditions. So this is basically an example how by just changing the interactions, we can play with the effective geometry of our system. And so you can think about it also. So let's take another example. So we want to make this more explicit that the geometry really changes. And so let's use, for example, again, the example of interactions at distance 3. And what you can think about it is basically these are 3 distinct chains with nearest neighbor interactions. And so we want to see, can we actually reconstruct this kind of geometrical structure of these 3 distinct chains? And for that, we look again, so we measure again correlations between the spins on the different sides, and we find this kind of distance 3 correlations that you would expect. And now you make an ansatz and say, okay, if it would be nearest neighbor interaction, can I find an effective coordinate system where actually these correlations decay exponentially? And there is a mathematical way to do it. And when we apply this to our data, we basically find that it's indeed these 3 distinct chains, and we can also reconstruct these couplings between these chains. So this is all extracted from experimental data. And so now we can be more fancy in another way. So let's, for example, take interactions at distance 6. So this would mean we have 6 distinct chains. And this is not very interesting itself because it's just a linear system. But now, instead of just using one frequency, we can also add in a second frequency. So we can, instead of only have interactions at distance 6, we can also add in a second modulation to the tri-field, which introduces interactions at distance 1, and basically connects all these ensembles between the chains. And now we have gained a second degree of freedom because we can also change the relative phase of this tri-field compared to this one. And so if we shift it by pi, then we effectively introduce, so if we have ferromagnetic interactions at distance 6, we introduce anti-ferromagnetic interactions at distance 1. And now if we look at the correlation, so this is how the modulation of the tri-field looks like in the end. And now if we look again at the correlations, we basically see anti-correlations if they one side apart and correlations if they're 6 sides apart. And now if we reconstruct the geometry, then it's basically this cylindrical geometry over here with these ferromagnetic and anti-ferromagnetic links. And so just to summarize a bit what else we can do. So what we also have done is like this completely antiferromagnetic triangular lattice that we can implement. And then what you saw on the title slide is this Mobius ladder, where you have ferromagnetic links along the ladder and antiferromagnetics on each rung. And so basically what this means is with this programmability, we can change the geometry, we can change the sign of the interaction, and we can also change the topology of our system. And so these are very interesting for future work, basically to study optimization algorithm, because this features frustration, and you can also do quantum simulation and look at information transport on these topological systems. And another fancy thing that we can do, which I can't go into very much detail, that we can also do instead of Euclidean geometries as these two, so where you can just plot them into three-dimensional space, you can also go to non-Archimedean geometry. And what I mean by that is, here the sense of geometry is different. Like here, it's best represented by this kind of a tree graph, where the distance between sides depends now on how high you have to go up in this, so where the last connection in this tree is. And this is very much connected to hyperbolic space. And there are toy models of quantum gravity, which basically use these kind of geometries. And now with our programmable interactions, we also have access to these kind of geometries, which are very hard if you just place atoms in space, in usual space-time. Okay, so with this, let me switch now to entanglement engineering. And so everything I showed you so far was basically classical. So it was all correlations between some kind of a collective spin on each side, and it was all classical correlations. Now we want to show that we can also indeed do something that's quantum and some entanglement engineering. And so let me first to show you how there's entanglement that's generated. So first, this pair creation process already generates a highly entangled state. It's very much connected to parametric down conversion. But to see this quantum effect, so let me write down now the full Hamiltonian. So there was one part I skipped before. And basically, there's not only the linear Zeeman shift in our system, but there's also a quadratic one. So here I plot again the 0, plus and minus 1 state, but I left out the linear Zeeman shift because it's for now not important. And I just used, and if you leave out the linear Zeeman shift, then you see that there is still a magnetic field dependent shift, which is this quadratic shift, which is much smaller, so it's just 280 Hertz. And it shifts the energy of the 0 state compared to the plus and minus 1. So generating an atom pair costs energy. And so this is now the full Hamiltonian with the XY interaction and quadratic Zeeman shift over here. And now to describe the system, so we heard before that spin 1 needs more degrees of freedom, and that's exactly the case here. So this is a spin 1 system. And so spin 1 is basically a symmetric addition of two spin 1/2. So instead of just having a dipole spin moment, Fx, Fy, Fc, you also have a quadrupole moment, which tells you how these two spin 1/2s are aligned to each other. And so you can find additional SU2 subspaces. And one of them we use here is this one where you have the spin in x direction on one axis, here this quadrupole operator on the other axis, and the number of your atoms in 0 at the z-axis. And on this sphere, what the quadratic Zeeman shift does, it induces rotations around the z-axis. And it's the same as the linear Zeeman shift introduces rotations around the fc-axis on your usual Bloch sphere. Here it does, here the quadratic Zeeman shift induces rotations here. And on this phase space, the interactions are nice to describe because they are a shearing term on this. So it's basically this fx interaction is a rotation around fx that depends on the value of fx in the mean field picture. And so it will flip sign as soon as fx changes sign, so you get this shearing. And if these two are of equal strength, then and you add them up, you basically get on a mean field level such kind of a phase space. And if you don't like these quadrupole operators, and then you can also just think about it in kind of a two-dimensional way and say, okay, fx and qyc, the important thing about it basically is that there are two non-commuting observables like x and p. So in your mind, you can always replace fx and qyc by x and p. And what these interactions do here, so our initial state where we prepare all in the zero is basically preparing your state at the north pole of the sphere. And of course, it has some quantum fluctuations, which are here depicted by the area of this disk. And via this interaction, what happens is it will redistribute the fluctuation. So it will get squeezed in one direction and it will get elongated in the other direction. And this is basically, these squeeze states are already a feature of quantum correlations inside your, between your atoms. Okay, so experimentally, we changed the system a little bit. We still have our ensembles, but we now just use 4 instead of 18, just to have more control over our system. And so what I told you in the beginning, like the cavity without the magnetic field gradient, it generates this all-to-all interaction. So you can think of these 4 ensembles just as one big ensemble. So you can just all add them up. And then if you look in this phase space, again, you, like before, you just have, you prepared basically a vacuum state with symmetric fluctuations. And so now when we drive it, we get to this squeeze distribution. And the way to measure it is now basically to always measure the fluctuations in fx while we rotate the state via the quadratic Zeeman shift. And if we do this for many repetitions, so for the for an unsqueezed state, you would expect that it doesn't depend on this rotation angle and always gives you the same value, which we normalized here to 1. And now if we use this squeezed state, after the interaction, we basically see that we have reduced fluctuations over here and enhanced fluctuations over here. And this is basically the signature of a squeezed state. And with that, we have shown that we indeed have quantum correlations in our system. Okay. So this is the first step to show quantumness, but now you want to go further. So now we actually want to say, where's now the entanglement? So there's just this bunch of atoms which we have averaged all together. What is now entangled in this system? And so for an experimentalist, the easiest thing to detect entanglement is via this recipe. So if you have two systems and you ask, so you have two systems A and B, and you want to know, are these two entangled? What you do is you basically measure two non-commuting observables, which in our case is this F and Q operator, and you measure them on each system. And then in the end, you compare, and so you know that they obey some certainty relations because they are non-commuting. And then in the end, you compare your results. And to detect entanglement, the question you ask is, how good can you use the measurement result, for example, in system B to predict the results in system A? And because quantum mechanically, if you add these, this F operator and subtract these Q operators, then basically the commutator cancels out. So basically, this you can measure in principle with arbitrary precision, but you need entanglement for that. And so if you look, if you show that this, in your measurement result, that the sum of these two variances is smaller than the local uncertainty relations, then you have shown entanglement. It's basically, if you look locally, then your variances is increased, while when you look at this non-local operator, kind of you get to this quantum mechanics-free subspace where you can predict it very precisely. And this ability to predict it better than the local uncertainty relation is the hallmark of entanglement. And this is what we want to show in our system. And so what we do here, if we initially add them all up, this is the same data I showed you before. And now we split the system into a left and a right side. And now instead of adding all up, like I showed you, the other way is you subtract the right side, the results on the right side. And for that, because the cavity only couples to the symmetric mode, this we expect this to be still a classical coherent state. And indeed, when we look in the measurements, we see that this basically shows no squeezing dynamics, has a little bit increased noise, but if we add the variances up from the minimum here and the maximum from this one, we get to something that's smaller than 2. And with that, we have shown that the A and B side are indeed entangled. But like the other mode still has kind of this classical behavior. And can we do something more? So can we get to a higher entangled state? And indeed we can. So the trick is, so we again start with the single mode squeezing. And now what we can do is, like in the readout, we can rotate this axis. Then we can do that we have local control in our system, and we can flip basically the spins on the right-hand side down to get to this orthogonal spin mode, and just use another pulse of our interactions. And with that, we can basically also introduce a squeeze state into this mode. And now if we evaluate these two modes, basically we get to something that's squeezed in one mode and also squeezed in the orthogonal modes. And with that, we can get to a much higher entangled state and to something that approaches more this quantum mechanics-free subspace, which you can use for enhanced measurements of, for example, the two conjugate observables. And just as a last step, which are pretty recent results, is what we can also do is a higher entangled state, which is these cluster states. And these cluster states are typically characterized by this graph. And one way to define it in this continuous variable system is that you need to verify these nullifier equations. So on each side, you have to make sure if you measure f on this side and you subtract the conjugate observables on the adjacent side, that this is in the limit 0. And you get this kind of adjacency matrix. And the trick how we can implement this is if we diagonalize this adjacency matrix, then we basically get a recipe what kind of modes we have to squeeze in our system. So there are 4 orthogonal modes in our system, which are shown here by these arrows. And so to get to this kind of cluster state structure, we have to squeeze them and we have to rotate the angle. So it's basically the same as I showed before, just repeat them also for the other modes. And then if we do this experimentally, we see that we can in fact squeeze all of these 4 modes. And we can also reconstruct the correlation matrix, and we see that this very much resembles the adjacency matrix over here. So just to summarize what we can do is, so we can get, if we just drive the cavity, we get to this global squeezing, which you can do for quantum metrology. If you have also local control, you can get quantum enhanced metrology for spatially extended field. Then we can have this multi-mode squeezing, where we squeeze basically, where we use 2 drive pulses to squeeze 2 orthogonal modes. And this you can use, for example, for also quantum enhanced insensitivity to some noise that you have in your system. And then we can also do individual squeezing of all of these ensembles, which you would use if you want to measure a field locally. And then in the end, what I've shown you is that we can do these generation of cluster states. So we have a wide variety of entangled states we can prepare in our system. And yes, so with this, I'm at the end. So I showed you how we used our cavity interactions to get to programmable interactions between atomic ensembles, and how we use this to basically engineer entanglement from a global to kind of multimode to a cluster state. And yes, with that, let me thank the team, especially the PI, Monica and Avika and Eric are the 2 grad students at the experiment. And with that, thank you for it.